Okay, so this is meant to be a very quick overview of Newton's three laws of motion. Now, chapter 4, what is on the textbook or in the textbook, goes through it in quite a bit of detail. We are going to talk about it in quite a bit of detail, but I wanted to give a quick overview of all of it so that when we start talking about it in class or any of those other places, through Teams messaging or email or whatever, so that you have a place to come back and at least look at all three of these. So Newton, rather brilliant dude from a long time ago, a couple hundred years. Basically, he was the first one to sit down and compile this work that was the amalgamation of lots of other scientists over the years. It's not to say he didn't do his own thing. He invented calculus to have all of the math check out in terms of his equations and his predictions and a lot of the other stuff that he did. But most of it was built off of observations that others had, and he was just the first person to visualize how it could all work together. So in his book, Mathematica Principia, he had a lot of great ideas. These are the big three to come out of that. And so he's obviously very famous, one of probably the more famous scientists that are out there, but these are his three laws. His first law is also referred to as the law of inertia. Inertia is the tendency for an object to continue doing what it was already doing. So this is the definition that the textbook might give you, but it's basically the tendency for an object to continue doing what it was already doing. If it was moving, it's going to continue moving. If it was not moving, it's going to continue not moving. And if you would like to change the motion of an object, if you would like to cause it to accelerate, speed up, slow down, turn, whatever, then you have to apply an unbalanced net force, non-zero, unbalanced net force. And that last part right there is crucial. It's that unbalanced force. And only once you have that unbalanced force, once you have that net force acting on the object, will it respond and accelerate in whatever direction that net force might have been applying it. So that was his first law, right? First law is the tendency for an object to continue doing what it was doing unless it's acted upon by an outside force. So, and that's really all inertia is. It's a property of mass. It's a property of matter, and it doesn't want to change. I like to draw the analogy or the comparison between it and a lazy individual sitting at home. If you don't want to get up and take out the garbage, you're probably not going to unless you're yelled at by someone else in the house. It could be a parent or a spouse to get up and actually take the garbage out. That would be the only way, right? So you need that outside stimulus. Otherwise, you're just going to keep sitting on the couch for a couple of hours and not realize that a few hours had passed. So inertia is like laziness in that regard, right? It's the tendency for an object to continue doing what it was doing. And that's obviously what his first law was saying. And if you don't have that unbalanced net force, outside force acting on the object, it's just going to keep doing what it was doing. And a lot of you guys figured this out too in the golf range gizmo. All right, if you remove gravity and you remove the air resistance and you hit that golf ball, it's just gonna keep going. This is something that we noticed with all the space probes that we've sent out there. Voyager 1, Voyager 2, Pioneer 10, all of those probes that have left the Earth's solar system, right? That have left our solar system are just going to keep drifting in space in a straight line path at the velocity that they had forever until something comes along and picks them up or they collide with something else. But that's going to take forever because space is so vast. It's, the probes that we have sent out there into deep space that have left the Earth's solar system, those will probably outlive the Earth, right? In about 5 billion years, the sun is going to swell. It will probably, if it doesn't consume the Earth, at least irradiate it to the point where life as we know it can't exist. And those probes out there in interstellar space, they'll just keep going. They'll still be moving at the same speed, right? Because there's nothing out there to act on them, most likely. So that is Newton's first law. Newton's second law, talk about friction real quick before we get to Newton's second law. There are four main types of friction. This is something that can cause the motion of an object to change even though we can't really see it. So four main types of friction are going to be kinetic friction. We already talked about this in the other set of notes that we had, the blue set. This could be sliding friction or rolling friction, right? Bowling ball or a soccer ball or a pair of ice skates for your sliding friction. It's the friction that happens between two objects that are moving, as opposed to static friction. Static friction is the initial friction that you get when you're trying to get something to move. Static friction is always going to be greater than kinetic friction. It's harder to get something moving than it is to keep it moving. Newton's first law and inertia, right? This is actually how all that works. If you've ever seen or heard of stories of people getting ejected from their vehicles in a car, if you're not holding on, or if you don't have a seatbelt to strap you into that car, then when you collide with another object and it forces you to come to a complete stop, like this car on the wall, then there are no outside forces acting on you, and your inertia is going to carry you through, carry you forward. You're going to continue moving in that straight line path that you had. So if you slam on the brakes in your car later on today and everything in your car goes flying forward, it wasn't because something pushed them forward. It was because there was a force applied to your car that caused it to come to a stop, but there was no force applied to those objects to make them come to a stop. Right? And so inertia is what carried you. It's not an outside force. It's just your tendency to continue doing what you were doing, which is part of the reason why seatbelts are so important. If the car comes to a stop, you should also come to a stop with the car. It doesn't usually end well if you don't. Newton's second law actually wound up being his equation. Now, he wrote his equation to actually be written out as A is equal to F divided by M. Your acceleration of an object is equal to, or is proportional to, the force acting on that object divided by the mass of the object. And that was what is exemplified in all the graphs in chapter 4. Right? They've got the acceleration as the slope of that line for the force and mass graph that they were making. But it worked out to be an equation, right? F equals ma. This is the same as y is equal to your slope multiplied by your value of x, right? Acceleration was your slope, your value of x is your mass, and y on the y-axis was your force. So it all comes back to those graphs. And this is where all of our equations for the entire year are going to be coming from. Now, you have to remember, and I mentioned this in the last video, that mass is going to be measured in kilograms. It's quantity of the amount of material that is present, whereas acceleration is how fast you were going divided by how long it took for that speed to change, right? It's how much your speed changed by divided by how long it took for that change to occur. Here's some practice problems. It's not meant to be something that is super complicated. Newton's second law is a very, very, very simple equation, right? So you get your mass of 2 kilograms multiplied by 5 meters per second squared. You're going to get 10. 2 and 10 is 20. 20 divided by 5 in that third example, that third row, is going to give you a mass of 4 kilograms. Your last one, if you have a net force, second to last one, if you have a net force of 10 newtons and 5 kilograms of mass, you're going to be moving at 2 meters per second. And then last but not least, 1 multiplied by 10 is still 10. So Newton's second law, very simple, very easy equation, F equals ma. That's really all it comes down to. Key behind this little chart, this little data table, was to show you the relationships between mass, acceleration, and force. If mass remains constant, like you see in the first to second row, but you double your acceleration, it took twice as much force to be able to make that occur. If you keep the force constant, like you see from the second row to the third row, if you keep that force constant at 20 newtons and you double the mass, then you get half of the acceleration. And so those are the kinds of relationships that this is meant to show you. This isn't going to be a slide we're going to spend too much time on, but this does show how Newton's second law supports the idea that all objects accelerate down to the earth at the same rate, right? If we calculate the weight of an object and then divide it by its mass, then you're able to figure out exactly how quickly they are accelerating to the earth, and it'll always be 9.8, right? We're not going to do this again. We're not going to walk through this again, but we're always going to be using 10 is essentially what we round it to in this class, but 10 is acceleration due to gravity still, forever and always. Newton's third law. For every action, there is an equal and opposite reaction. This is basically a statement of all forces come in pairs. There's always going to be two forces. You have an action and a reaction. So in the case of firearms or ballistics in general, this is really easy to see because you always have what we refer to as recoil or kickback, right? It's always going to push against you as well. This is why you've got the really large stocks on the back of rifles or shotguns, or why everyone, when you fire a cannon, you kind of step away while it's firing, because we've all watched it. It could be a pirate TV show or movie or something about Napoleon or the Civil War. It doesn't matter. Those cannons, when they fire, the whole cannon gets kicked back. It's the exact same idea, right? You're applying a force to a small object to get it to move forward quickly, and then there's a really small recoil compared to how quickly the other object was moving. So this is Newton's third law in a nutshell, right? There's always two forces. If you push on the wall pushes back. I sit down in the chair pushes back. Those are always going to be pairs. If one force becomes significantly larger than the other, then one might overwhelm the other and you could fall through your chair or fall through the floor if your floorboard's dry rotted or whatever. But you've always got these action-reaction forces, and that's the main idea. In nature, we see it all the time, right? Fish as they swim. In fact, if you ever went swimming, this is what you do. You cup your hand and you push the water down, away, and behind you. And as you push the water down, away, and behind you, you are propelling yourself forward. Fish do the exact same thing with their flippers or their fins, whatever you want to call them. I'm not a biology person, but it's the same idea. The larger the surface area, the more water you can push and displace out of your way, the faster you're going to be propelled forward. But this is how fish are able to swim around, or you are able to swim around. Birds do the same thing. The difference, though, is not only are they trying to keep themselves up in the air, opposite gravity, naturally. They don't have the whole buoyancy thing that fish kind of do to help them out. But they also have very, very, very large wings and wingspans relative to their body size because the atmosphere is a lot thinner. So you have to displace more air. By pushing down and behind you, they're able to generate a lot of lift. Now, they've got other really cool biological things going on, like the fact that their wings are 2/3 of their body size or surface area. All of their bones are hollow and other really cool things like that to make them lighter and more capable of flight. But it's still the same principle. They push down and backwards behind them, and that's what is allowed to provide that lift in order to keep them up in the air. Baseball is the exact same thing. You have felt this if you've ever tried to play baseball in the winter or when it starts getting really cold, either late fall, early spring, depending on whether or not you're doing baseball or softball. But the same idea is true. If your bat hits the ball, oftentimes when it's really cold, you can feel it. If it hits it the right way, you can feel that little vibration go all the way up your forearms, and it kind of rattles you for a moment. It's the exact same scenario. The bat hits the ball, and the ball hits back on the bat. The two of them come in pairs. Even your car does the exact same thing. In order for your car to propel you and everything else in your car forward, the tires have to push on the ground behind you. So next time you're driving your car or watching someone pull away, pay attention to the direction the wheels are spinning. They make contact with the ground and then push backwards behind the car towards the trunk to propel the car itself forward. It's always Newton's third law, equal opposite. The tires push off the road pushes back on the tires, propels you forward. Even rockets, right? I guarantee you, if I were to ask you guys in class, why do rockets fly up into the air, that some of you, even if you might not say it, will be thinking to yourselves, well, they push the giant pillar of flame and smoke. They push up off of the ground. And at the beginning of the launch, sure, it does look like they push up off of the ground, but at some point, the ground is no longer beneath them. At some point, that giant flame of fire coming out of the back of the rocket is no longer in contact with the ground. So why then does it continue to accelerate upwards? It is literally just the force of all of that air being expended out the back of the rocket that propels it forward. It doesn't need to push off of anything. If you don't believe me, blow up a balloon and let go of it. Let it fly around your room. That air escaping that very narrow opening on the balloon isn't pushing off of anything except for it's literally just the force of the atmosphere rushing out of the balloon, propelling the remainder of the balloon forward. That is it. That is all. Newton's third law always has forces acting in pairs. There's always two. And then last but not least, one of the main ideas of this class is the difference, or this unit, is the difference between mass and weight. They are not the same thing, even though we Americans like to use them interchangeably. If you check out the back of a semi-truck, you'll see the maximum mass that trailer is capable of holding measured in kilograms next to its weight in pounds. They are not the same thing. Right? It aggravates me. Most people don't notice or care, but it does. It aggravates me, right? Kilograms and pounds are not the same measurement. They do not tell you the same thing. Mass is the amount of matter or material that is present in that object. Volume can change, so you can have different densities, sure, but mass is the amount of stuff that is there. You could describe that stuff as cells, atoms, molecules, subatomic particles. It doesn't matter what you want to describe mass as. We use kilograms to measure it. It is the quantity of stuff that is there. Weight is a force. And this is why in the last set of notes we always described weight as the force of gravity. It is F sub g. It is how that object is influenced by the planet's gravity around it. If you were to take a 10 kilogram mass here on Earth to the moon, it will still have a mass of 10 kilograms, but its weight will be significantly less because the moon is a lot smaller than the Earth is. It has a significantly smaller acceleration due to gravity. So they are not the same thing. If we want to calculate an object's weight, you still have to multiply its mass by the acceleration due to gravity. So if I wanted to take my weight, I'm around 90 to 95 kilograms of mass, that is Mr. Willis's mass. And if I wanted to convert that into a weight in newtons, then I would be somewhere on the order of 900 to 950 newtons. Now that works out to be like 200 pounds, right? These are all just different ways of describing the same thing with different units. It's like a yard versus a foot. They don't have to be the same, but they are similar. So oftentimes people will get answers on the first homework assignment for this unit of, 600 newtons for someone's weight. And they're like, no, it can't be 600 pounds. It's not. Newtons and pounds do not measure the same quantity of weight. They are both measurements of weight, but it's like arguing 15 yards versus 45 feet. They are the same physical distance, right? So my 900 newtons is the same as 200 pounds. I'm just using a different unit to describe it. So if you get large values of newtons for an object's weight or a person's weight in this class, don't panic, don't hesitate. I'll often describe roughly 1,000 newtons as a Mr. Willis, right? So if you get 25,000 newtons for an answer, I'll say that's like 25 Mr. Willises, right? Just to give you guys some sort of sense of scale. It really doesn't matter. Just make sure you're checking your math and you're doing well with it. If you go and check out the actual set of PowerPoint notes, you'll find here's a link to Bill Nye's fantastic, it's actually just an excerpt from that show or from that episode on mass versus weight and the laws of inertia, but it's a pretty good one. And obviously you can go down that YouTube rabbit hole to see what more Bill Nye has to say. But that was about it. So that was an overview of Newton's 3 laws. First law is the law of inertia. Things will continue to do what they are already doing. Nature is lazy, is my way of summarizing that one. His second law is F equals ma. That is your calculation. And then the third law, forces always occur in pairs. Always, always, always come in pairs. That was it.